Good morning, this is Team 35. Our project is integrating concept embeddings into vision language models. For this project, we aim to overcome the limitations of token-level vision language models like CLIP and BLIP, which tie representations to specific vocabularies and often miss high-level abstract semantics by mapping images directly into a shared sentence-level concept space. We can capture richer language-agnostic meaning that better reflects human reasoning. This has immediate impact in multilingual captioning and robust zero-shot retrieval. While prior work aligns pixels and tokens, our novelty is in regressing visual inputs into fixed-size concept of embeddings, enabling truly modality-agnostic holistic representation. Our work is a novel approach applied to COCO 2017 with 118,000 images. Each image has 5 captions. We pre-compute Sonar embeddings for our caption and train ResNet 50-based encoder to regress images into the same space. We assume minimal pre-processing, just resizing and normalization, and apply standard data augmentations like flips and color jittering during training to improve generalization. We train our image encoder in a classic teacher-student setup. The teacher is a pre-trained Sonar text encoder that produces fixed-length 1024 dimensional embeddings for each caption. The student is a ResNet 50 backbone whose final fully connected layer we replace with 1024 dimensional projection head. To begin, we warm up the student with a random caption mean-squared error loss, sampling one caption embedding per image and regressing the image embedding toward it. Once the model has converged on this simpler objective, we can apply other losses to fine-tune it. At the inference time, we never generate tokens one by one. For captioning, we simply run a off-the-shelf concept encoder over the image Sonar embedding to produce sentence in one pass. For visual question answering, first encode the question into Sonar, concatenated with the image embedding. We feed the joint vector into a small classifier that predicts the answer in concept space. Because we operate entirely on the embedding level, our pipelines are both faster and more semantically coherent than traditional token autoregressive approaches. So these are the loss function we used in our training processes. Our evaluation spans both downstream captioning quality and direct embedding alignment. For captioning, we report BLU4 and the CIDR on the COCO validation split. As a semantic alignment metric, we track both the pure angle-based loss and the regressive style error between image embeddings and their true Sonar captioning vectors. When comparing against the strong off-the-shelf baseline, Blip on Coco yields BLU for our 39 and CIDR of 130. In our own validation set embedding alignment tests, we observe a validation of cosine embedding loss of approximately 0.33 and a random caption mean square error loss about 4.45 to the power of -5. We also compute the cosine similarity matrix across the images, 5 golden captions, finding an average of the shelf of diagonal similarity of only 0.394, indicating surprisingly weak angular alignment even among human written descriptions of the same thing. So in conclusion, we build the concept level embeddings capture higher order semantics, and the concept level embeddings do not necessarily follow the cosine similarities. Compared with contrasted loss, mean squared error might be better. For future work, we plan to further fine-tune a vision encoder with mean square error loss and verify the encoder with different metrics. We also want to apply an encoder for image captioning and visual question answering tasks to compare its efficacy to Blip. We also want to integrate speech decoding via Sonar multi-model decoder. That's all my presentation. Thank you.